Okay, picture the grandest, absolute, most mind-bending physics concept you can possibly imagine. Albert Einstein's theory of space-time. Now, imagine contrasting that magnificent, universe-altering idea with a pair of old spandex bike shorts. I know, it sounds totally absurd, but today in this explainer, we are exploring gravity visualized, and we're doing it right on a classroom table.
So that brings us to a really fascinating question. How do you demonstrate Einstein's greatest theory for just $100? Well, we're going to dive into how one incredibly inspiring teacher brings the vast, sweeping mechanics of the cosmos to life on a remarkably tight budget. As you'll see, a few everyday items can completely transform how we understand the universe, proving that sometimes the simplest tools actually yield the deepest understanding. All right, let's dive into Section 1, Bending Space and Time. To really get this demonstration, we first got to tackle this somewhat intimidating concept. According to general relativity, matter actually bends space-time. So when you drop a mass somewhere in space, it literally warps the environment around it. The absolutely crucial point here is that objects aren't feeling some invisible, traditional force of gravity pulling them like a magnet. Actually, scratch that. It's more like they're simply moving along, following the natural curvature created by that mass. Gravity is really just objects responding to a warped environment. And to model this incredible theory, we are looking at some seriously mundane materials. You just need a sheet of stretchy lycra or spandex. The teacher actually notes you can get this from a spandex website for about $20 on sale. Then you grab some PVC pipe and a few bungee cords to build a frame to stretch it tight. Finally, you throw in a heavy central mass to act as our sun and some standard little marbles to be the planets. When you plop that heavy central mass into the middle of the stretched fabric, it creates a physical dip. And boom, that dip is our warped space-time. Moving right along to Section 2, the physics of orbits. So if you take a marble and do a straight drop onto the fabric, it just goes zooming right down the slope, drawn directly to that center mass. But if you give that exact same marble a sideways push, something magical happens. It creates an orbit. It just rolls around the curvature of the dip. Now, in this physical classroom model, friction obviously causes the marble to lose energy and eventually spiral in. Our actual solar system doesn't noticeably lose energy like this, but the visual perfectly captures the basic mechanics of how an orbit works. You know what's really fascinating? This gravitational interaction actually goes both ways. While a huge mass bends space a ton, those tiny marbles, like our planets or moons, they also warp the fabric slightly. In reality, the heavy central mass feels the warping of the smaller marble too. As noted in our source, the moon literally makes the Earth wobble around a point about 3/4 of the way from the center of the Earth. We usually kind of ignore this tiny movement when looking at satellite motion, but mathematically and physically, it is absolutely always there. Next up, Section 3, One-Way Solar System. Now, what's really interesting about this slide is, have you ever wondered why all the planets orbit the sun in the exact same direction? Well, it turns out it didn't start that way at all. If you take a handful of marbles and just toss them onto the spandex in completely random directions, you initially get this chaotic debris. But inevitably, a slight preference emerges. Maybe you threw slightly more marbles with your right hand than your left. Because of that tiny preferred direction, the outliers going the wrong way end up colliding with the others and just get eliminated. Their momentum is canceled out. Eventually, all that's left is uniform rotation. And amazingly, just tossing marbles randomly on this fabric results in this uniform one-way orbit about 90% of the time. What really solidifies the learning here is the connection to modern tools. High school students often use computer simulations, like the PhET My Solar System program, when they study special relativity. And let me tell you, students are completely blown away when they see this physical $20 piece of stretchy lycra behave exactly like their highly programmed digital physics simulations on the computer. It brilliantly bridges the gap between the screen and the real world. Okay, Section 4, the Apollo Figure 8. You've probably seen those big, hard plastic gravity wells at science museums, right? Like the Exploratorium, or even at shopping malls where you drop a coin in to watch it spin. They are super fun, for sure, but they have a massive limitation. They're fixed shapes. Our spandex model, on the other hand, allows you to place multiple massive objects on it. You can drop down a heavy mass for the Earth and a slightly smaller mass for the Moon, which warps the fabric in two distinct dynamically interacting locations. Because we can have two masses, we get to demonstrate entirely different mathematical paths. A simple orbit is just your standard elliptical loop around one body. But a free return trajectory, that is a highly complex figure-8 path around two bodies. And get this, this is exactly the trajectory the Apollo astronauts used to travel safely to the Moon and slingshot right back to Earth. I do have to add a quick aside here. The teacher totally admits that getting a marble to smoothly trace that perfect Apollo figure eight on the spandex is not easy. It takes a ton of practice, super careful adjustment of those PVC clamps around the edges to get the tension exactly right, and a very steady hand. But man, when it works, seeing that historical mathematical trajectory play out on a piece of fabric is just breathtaking.
Finally, Section 5, repairing the fabric.
I absolutely love this story from our source. Because the Lycra comes in narrow rolls, you actually have to sew pieces together with stretchy thread to make it big enough for a whole class to gather around. And, sometimes it rips. The teacher tells this hilarious anecdote about coming in early to set up. He's literally underneath the table, manually sewing the fabric back together. His principal walks into the room, hears the rustling, bends down and asks what on earth he's doing under there. The teacher just looks up and deadpans. I'm repairing a rip in the fabric of space-time. Just a brilliant, dedicated teacher moment right there.
And this brilliantly illustrates how flexible this whole setup is for spontaneous questions. Like one year, a kid read about dark energy, the force that makes the universe expand and pull apart. The student asked how that would work. The teacher's solution? He literally just reached underneath the fabric and pushed up. By creating a hill instead of a dip, all the marbles instantly flew apart, beautifully simulating the exact effect of dark energy. Just a quick word of warning from the teacher, though. Definitely don't let students go under the table to push up while someone else is dropping a heavy central mass on top, or they might get their own personal space-time warped.
But honestly, the absolute most powerful takeaway from this teacher's method is the power of unstructured play. He gives a brief 10 to 15-minute spiel to explain the concepts, and then he just steps back and lets the kids play. It's this unstructured play that drives true, lasting educational discovery. By just messing around and experimenting with the marbles on the fabric, the students independently discovered how to make an Earth-Moon system themselves. They were so excited simply because they figured it out on their own, totally hands-on.
So we have to return to this incredible number for a second, $100. If you buy all the PVC parts, the bungee cords, the Lycra, the heavy masses, and the marbles, it costs roughly $100 to build the whole shebang. That is the sheer, incredible accessibility of this model. It proves you absolutely do not need a $1 million lab to create something profound and deeply engaging for learners. Which leaves us with a pretty provocative thought. As the teacher points out, general relativity, arguably one of the crowning achievements of modern science, is probably not on the state standardized test. But does a lesson have to be on the state standardized test to be worth teaching? When you see the awe, the discovery, and the deep physical understanding that comes from playing with a $100 piece of spandex, the answer is a resounding no. This teacher fits it in right after the state testing is done, and it instantly becomes a day the students will never, ever forget. It really challenges us to remember the inspiring value of true hands-on educational discovery over simple test prep.